Hi, I'm Bob Doyle, the information philosopher, webcasting from my ITV studio in Cambridge, Massachusetts, and hoping to reach philosophers and scientists around the world to help me solve some great problems in philosophy, in physics, in biology, and in psychology. Still learning to move around here. I also hope to reach any of you wondering about the deepest nature of reality and our place in the universe. We live in the information age, but I find that very few philosophers or scientists understand the nature of information. An abstract quantity, I will claim, is the stuff of thought. Information, I will show, is neither matter nor energy. Information needs matter to be embodied in our brains, for example, and it needs energy to be communicated, like this lecture coming to you over the internet. But matter and energy are conserved quantities. It may be hard to believe, but the total amount of matter and energy today is the same as there was at the beginning of the universe nearly 14 billion years ago. And if the stuff of the material world is just a fixed total amount, what can possibly explain all the evolutionary change that we see? New things emerging under the sun. I'll explain those cosmological changes by showing that information and order in the universe have been increasing since the beginning of time, despite the second law of thermodynamics. Change, I will show, is the arrangement of matter, the atoms and molecules, into what I call information structures, like the galaxies, the stars, and the planets. Well, stars are under control of physical forces like gravity, but living things, you and I, are growing dynamic information structures under our own control. I'll show that it's information processing from the DNA in our cells to the thinking in our minds that controls the flows of matter and energy through every living being. Well, welcome to the Information Philosopher on my first Friday lecture, which is going to be devoted every week to the work of Albert Einstein. My other lectures tend to have a philosophical bent, and as you might imagine, my talks about Albert Einstein will have a very scientific bent, and we'll be getting into some very technical issues at some point. I expect to be lecturing on Einstein for many months because there's an awful lot to say about him. What I want to tell you mostly is that I've been reading Einstein for decades now and have always thought there was something very deep in his work, which tended to be historically ignored by his colleagues. Many of the famous founders of quantum physics, like Werner Heisenberg, Niels Bohr, thought that Einstein had sort of grown to be suffering from old age and not appreciating the new modern versions of quantum mechanics. In fact, there's this phrase that there was before Heisenberg and Jordan and Dirac and Max Born, there was an old quantum mechanics, which had been associated with the ideas of Niels Bohr and his Bohr atom, in which there was a nucleus and then orbits, and in successive orbits, which were imagined to be little planetary-like orbits going around the nucleus in the middle, there were jumps from level to level in which radiation was given off in discrete amounts, according to some thinkers, like Einstein, and given off continuously by other thinkers, like Bohr, who rejected Einstein's idea of a quantum of energy. This is a very complicated subject, and for me to try to give you the sense of it quickly, I will just say, I will look at my next book, which is my God, he plays dice, an argument that Albert Einstein really invented most of quantum mechanics. Let me go to one of my close-up views of the Einstein book. And this is, of course, a rather strong claim, especially since Einstein is well known to be the most serious critic of most of quantum mechanics. In the later years, as Heisenberg developed his uncertainty principle and his most important work, which was the ability to calculate quantum energy differences between the energy levels in the hydrogen atom, for example, and therefore was able to predict the light intensity that's given off when an atom jumps from level 2 down to level 1, or the energy that it absorbs when it goes up from a level 1 to a level 2, 3, or 4. So when Einstein encountered these works, he was very puzzled by some of the aspects that the founders thought was necessary to explain quantum mechanics, but they made quantum mechanics into a statistical science. And that Einstein expressed worry about by his famous phrase that God does not play dice. Now, we have no reason to think that the God of Einstein was a theological entity, an agent in charge of the world. It rather seems to have been the notion that the world was managed, quote, managed by rational laws of nature that gave an explanation to everything, and that chance events seemed out of order in such a universe. I'll show eventually that Einstein, although he is cited for many decades, the notion that God doesn't play dice, in opposition to a chance nature in quantum mechanics, what's called indeterminism. I'll also show that in his later years he definitely eased off on his concerns about whether quantum mechanics involved genuine probability, genuine indeterminism. And this, in part, was because he was the one who first discovered indeterminacy in quantum mechanics, full 10 years before Werner Heisenberg's uncertainty principle. So let's go back to this book and take a little bit of a few words about why I think this is very important. That's a nice zoom in here, right? So I'm going to ask this question and then try to answer it over the course of many, many more lectures on Albert Einstein. Is it possible, I say, that the most famous critic of quantum mechanics actually invented, or discovered, we might say, most of its fundamentally important concepts? Now this, I believe, is a really radical notion because the way I learned quantum mechanics, taught in my classes at Harvard back in the 1960s, all started with Heisenberg and Dirac and Jordan and Max Born, all these people who were the founders of quantum mechanical theory, as it was a form of calculating. It was a form of calculating what we know about quantum structures. Now, Einstein really never had all that much interest in the calculations, although he famously did some enormously important computations and calculations to prove, for example, that the perihelion of the orbit of Mercury was strangely different from what Newton's laws suggested it should be. And Einstein's theory of general relativity was an enormous calculation, which he did with a friend who helped a great deal with it. But at the bottom line was that he was able to show that the angular extra deflection of the orbit of Mercury going around the sun every year was accounted for exactly by his general theory in a way that Newtonian gravitational theory could not understand. And so gravitation theory became Einstein's theory of general relativity, the famous notion that space itself is curved and it's contributing to this behavior, which, while very small, was indicating that the nature of reality was quite different from a simple Newtonian reality. Okay, but I'm going to try to say that Einstein did a number of things, and they're summarized here briefly. First, Einstein was the one who quantized light energy. That is to say, he showed that it came in lumps or packets or quanta. He called them Lichtquanta, light quanta. They're known today as photons. And that is usually credited to the work of Max Planck, who studied a radiation law in 1900 and decided that if he assumed the math of energy was discrete, he would be able to prove the shape of the law of radiation at different colors at different temperatures. But I'm going to show you that it was not Max Planck who actually made this deep assumption that the energy was quantized. And for Max Planck, it was a heuristic mathematical trick, a lucky trick that he happened to stumble on. And we, of course, know very famously that Einstein argued that matter and energy are interchangeable, with his wonderful famous formula that energy is equivalent to the mass, the matter of an object, multiplied by the velocity of light. This was, of course, amazing, as the velocity of light is an enormous number, 3 times the power of 10 to the 10th centimeters per second, which means that 1 gram of matter, if it's converted to energy, it will release a vast amount of energy beyond anything imaginable in chemistry. And it was, of course, a prediction that in the future we might liberate that energy when atoms split or are combined in hydrogen fusion. So Einstein did those wonderful things. We sort of know he did them, but we don't associate him that much with quantum mechanics. So I'm going to also show that he was the first scientist to see many of the most fundamental aspects of quantum physics. For example, the physical derivation of Max Planck's radiation law was only done by Planck with a heuristic, a lucky guess, he called it, about the shape of things, whereas Einstein did the first derivation from first principles, his own first principles, which involved quantization of energy. Then there's a concept called nonlocality, which involves, already in the earliest days, an idea about instantaneous action at a distance. Later on, much later, this work I'm going to describe to you was done in his very first papers in 1905. There were 3 famous papers, one on relativity, another one on the particles of matter jiggling around in the Brownian motion seen by chemists, and the most important one, in my view, was a hypothesis that light came in quanta. But already in that paper, we'll see that he was worried that there was a sign that something was happening in an experiment, which, let's switch away just to me for a moment. He imagined an experiment in which light went off in all directions from a shining light system. And in those days, the light was supposed to go off in all directions, okay, as waves in the theory of the 19th century. But the important thing is that it went off in all directions. And yet Einstein was able to show that experiments had indicated that when the light was absorbed, it was absorbed all together in a complete package at just one single point, rather than being absorbed everywhere. And that was the first indication that although something had gone out in all directions, okay, so Einstein should have been able to expect that there was an influence of that light throughout the volume where the light was being distributed. Nevertheless, by winding out in a single point at a certain moment, all that wave information that had gone out spherically in all directions seemed to suddenly disappear. We call it today the collapse of the wave, as if the wave, while it filled the whole space, suddenly appears at one place only. That was the first insight into what Einstein called non-local events, non-local processes, so that the behavior of the physics with, say, the particle being absorbed depended on things that were very far away. That didn't agree with his notion that physics ought to be local and that everything that goes on is really a consequence of the event in space and time and a little tiny volume around it where other events could be contributing to what's about to happen. So what we have here is an idea that something's traveling throughout space, maybe very, very large distances. And that will turn out to be very important when we come to 30 years later. So let's go back to my little listing. A year after his first insight into this strange idea that the wave is going in lots of directions and yet it winds up in a single point, something he later called spooky action at a distance, because it is to this day not completely explained. The next year, he saw that atoms, especially atoms arranged in a crystal, a largish object, in what he came to call solid state of matter, in which there's a large number of atoms all bumping up against one another, he saw that there was a structure inside, that there were energy levels inside, perhaps inside the atoms. Something that was going to appear again in the work of Niels Bohr in 1913, 7 years later. Then in 1909, the notion, you can see it in his writing of 1905, but in 1909, he very clearly seems to say that light seems to have both a wave character and a particle character. And moreover, that the wave part collapses in 1909. That subject will become a real mystery in quantum mechanics, but let's notice, later on, in the late 1920s and so forth, and all the modern interpretations and all the philosophical questions that surround the collapse of the wave function. And as we saw earlier in the week, David Chalmers and many other philosophers and quite a few scientists think that that collapse is somehow related to events in the mind and consciousness, and the notion of a quantum collapse are connected by lots and lots of thinkers, and we'll get back to many of them. But anyway, in 1916, Einstein, after Bohr had proposed his model of an atom with different levels, and remember, the level idea was something that Einstein had already seen something of in 1906, but in 1903, Bohr put up the level idea, the levels, multiple energy levels inside an atom. And in 1916, Einstein calculated the probabilities of transition between the levels, whether it's emission, in which an electron falls from a higher energy level to a lower one, or absorption. He calculated them and showed that they introduce indeterminism whenever matter and radiation interact. That single paper made quantum mechanics a statistical theory. That's 1916, 1917. And that was a paper in which he wrote that it seems as if there is a great difficulty, a fault in the theory, because it introduces chance into physics, something that Einstein, as we'll see, never really cared, for the simple reason that God does not play dice, as he put it, for many years. And then, maybe 9 years later, Einstein, working on the basis of a suggestion by the Indian physicist Bohm, he found out and then proved that elementary particles like electrons and of course photons are indistinguishable from one another. Now, indistinguishability had been an ancient argument in philosophy, in metaphysics, because it was the question of identity. What is the principle of identity? What are the conditions that establish the identity of any entity in the universe? suddenly Einstein was showing that because the two electrons are, in his sense now, identical to one another, it turns out that the mathematics of the statistics of these particles is quite different from what we would assume if the particles could be distinguished from one another. And this introduced a new theory of quantum statistics, in which some particles were called fermions after Enrico Fermi, and some were called bosons after Bose, who had suggested this mathematics that he'd done to Einstein. Sadly, they're not called Einstein-ons, too awkward, I guess, but as with the overall flow of ideas through the ages, most of these things that Einstein discovered have names on them that belong to other physicists. And so in this case, the boson statistics, which led Einstein to this most amazing insight that as the temperature gets lower and lower, these bosons come to behave like a single sort of liquidy fluid that's like nothing else ever understood, ever seen in physics. And today these Einstein-Bose condensations are a very, very important part of extremely low temperature physics. And then finally, 30 years after first suggesting action at a distance or seeing this non-locality, Einstein wrote this famous paper with his colleagues Podolsky and Rosen about what became to be known as entanglement of those identical particles when they interact, and a characteristic that came to be known as their nonseparability. Nonseparability suggested to Einstein that particles traveling away from a center where they had interacted would remain somehow in contact with one another. Now, he, in this paper, attacked the idea because he didn't think it reasonable. But the fact is that Einstein could see that particles which were leaving a center, two particles that were originated in a single event that gave off an electron going this way and another electron going that way, Einstein saw something very strange in that. Now, that paper was attacked, almost debunked, and the attackers included Bohr. They included Schrodinger, although Schrodinger was a good friend of Einstein, and they wrote back and forth around this issue in the next several months. And Schrodinger was right about one thing that Einstein didn't want to believe. This is a kind of characteristic of this curmudgeonly Einstein, that he didn't like a lot of these things that seemed to be in quantum mechanics. But let's remember this point. Einstein was the first one to see this notion of entanglement. And that it is this notion that leads to many of the most interesting modern mysteries and new capabilities for quantum mechanics, including the idea of what's called quantum information, quantum computing, and the idea that particles can be, in a way, connected with one another even though they are great distances apart. Some people take this to the level of saying, well, one particle could talk to another particle and have an influence on it, effectively sending information between the two particles at faster than the speed of light. They even suggest that maybe they could use this kind of influence, action at a distance, to teleport something from one place to another. And the teleportation papers, if you read them closely, really are normally just arguing you can transport information faster than the speed of light. Now, in my view, all of this is mostly nonsense. But I'm definitely not in the norm of reading what's going on in some of this wonderful new quantum stuff. And these ideas are the stuff of major papers and articles, especially in the popular scientific literature, which means that most anybody who's read about these things might be interested in an alternative way at looking at these things, something I hope I'll give you, and I'll try hard to help you see these things as I think Einstein saw them. I sort of thought of a slogan, a subtitle of my work was looking at physics, looking at reality through Einstein's eyes, because there's no doubt that Albert Einstein had a much better insight into the workings of reality than any other single thinker. And I would especially like to argue that his arguments for what he called an objective reality, it covered the idea that things were local reality as opposed to non-local and this non-separable and so forth. But the idea is that something was going on deep down at the quantum level, which wasn't really being explained by the theories of the founders of modern quantum mechanics, the ones like Heisenberg and Schrodinger, who came up with methods to calculate really incredibly accurate calculations. So they deservedly have the reputation, the founders of quantum mechanics, of having brought into this world the most accurate theory of the physical world that we have. And I don't mean to take anything away from them in this incredible work when I tell you that they did not want to try to see what might be actually going on at the quantum level. And the famous Copenhagen interpretation of quantum mechanics, which for decades was the only way of thinking about quantum mechanics, puts up an intellectual barrier between us and quantum reality, saying things like, don't even ask what's going on in the interactions between matter and radiation. Don't try to visualize. Schrodinger had this great hope for visualization. In German it's called Anschaulichkeit. And he thought his wave theory of what was going on at the level of quantum reality gave us a much more beautiful picture of what's going on. Everything would be reduced to waves. And the particles were just sort of riding along with the waves in some theories, notably that of Louis de Broglie, who suggested that the particle was just somehow riding along the wave, that the wave was a pilot, a guiding, not a force, because we don't imagine this has anything to do with forces, but that the wave was guiding the path somehow and moving it along its path. And then Schrodinger developed his famous equation for the evolution, the time evolution, meaning the way the wave moves in time. And as I said, Schrodinger thought that he had seen what was really going on. Now the surprising, at the nature of reality, now the surprising thing is that Schrodinger went all the way to believing that the wave was the fundamental thing that was going on in the universe, and there really are not any particles at all, which became quite strange. He even attacked the idea of quantum jumps, that things jump from orbit to orbit in the Bohr atom and so forth. So all of these figures, great contributors to the theory, Heisenberg, Max Born, with their calculation abilities, Schrodinger with his idea that everything was being managed by the motion of a wave around in the world and measurable in experiments. And then, of course, Einstein, who all the way along had a rather different view of looking at everything, and he was just unable to communicate what he was thinking for most of those years. Nevertheless, his last major important contribution, Einstein Podolsky Rosen, called the EPR experiment, because it did suggest an experiment, for years just was considered to be ridiculous and not worth thinking about by the standard quantum physics of the 1940s, 1950s, 1960s, when I studied quantum mechanics at Harvard. But then sometime in the, I think I get the date correctly, sometime in the 60s, John Bell came along, and he imagined there could be an experiment to test Einstein's criticism of quantum mechanics, especially the entangled particle idea. And he suggested that the experiment could be done in such a way that it would show that Einstein was right and quantum mechanics was wrong. Now, there were other thinkers who'd given a good deal of attention to this entanglement business, notably David Bohm, who had a kind of radical view of what quantum was telling us and developed his own somewhat obscure theories. But he wrote a wonderful textbook on quantum mechanics, one that I also used, written in 1952. But then he seemed to step away from what he knew about quantum mechanics and added the idea that maybe high velocity things faster than light were involved in sending signals between the two separating particles in the entanglement experiment. And if he could do that, he could then explain the mysterious things that Einstein saw in quantum mechanics and objected to. He had met with Einstein and thought that Einstein had encouraged him, David Bohm, into thinking about these things and possibly coming up with explanations that would restore determinism to quantum mechanics, which is one of the things Einstein thought about a good deal. And yet the notion of what Bohm was talking about was not realized as an experiment until many years later. It was first John Bell who proposed the way an experiment could be done. Bohm thought it might be done with two electrons separating, and Bell thought it might be done with photons separating and going through polarizers to see whether they had the same polarization, even though they were very far apart. And then there came a series of experimenters in California and in France in the 1970s, I think, maybe later. I should give you more on that when that comes up. But all their experiments confirmed not Einstein's concerns, but the accuracy of quantum physics. That quantum physics did include everything that Einstein was worried about. Mind you, he saw it, but he didn't like it, and that's going to be a theme throughout all of our lectures. Now, I would like to say that there are four things, really. Let's see if I'm on. Four important things that we can credit to Einstein as modern problems where he originated it, and eventually it's been shown to be the case, and he was either worried about it or actually opposed to it. So he stood against it for many years. But these four, think about where I could summarize these four for you, are going to be a continuing theme in our study of quantum physics in general. So let me see, right now I'm showing you this page, Albert Einstein, and I could go over to my page here. Oh, and that's not the one I want. I'll go back to Einstein. And that's not the one I want. So here I am, probably this one. That will do. But I'm hoping to show you these four particular problems. We saw them mentioned on the back of the book, and maybe I should just go back to the book for just a moment. What we'd like to talk about is the collapse of the wave function and the idea that particles of matter consist of both waves and particles in some sense. Those are the first two. And the other two are the idea of entanglement. Here I've got my little notes on the ones I wanted to suggest to you. And something called the Two-Slit Experiment, which Einstein normally thought about just one slit and particles going through that slit, but for a long time there has been the idea of a two-slit experiment. And I'd like to show you about that two-slit experiment. Let's see, I've got it here. And back to SR. We talked about this briefly yesterday, and it's the notion that particles, or waves in this case, can go through a slit in a wall, and that they will then interfere with one another. Now, the question is, how can one particle go through one slit? And the notion of the modern two-slit experiment is that we let only one particle go through these slits at a time. How can one particle going through one slit create a wave interference pattern? So I think somewhere down in this page I've got, first of all, Richard Feynman's lecture on the two-slit experiment. And with 15 minutes to go, we can take a look at that. I also have a little video done by someone else on this two-slit experiment. It's way down in this page. We're going to study a lot of this. But here's an animation of the two-slit experiment with some comments. So let's listen to this. Okay. You see particles are fired from a gun and they're hitting two slits in a wall. And they're gradually accumulating on the back wall. And if you look closely, I think they'll bring us into it, and they'll see some pattern back there. But now when we think about this as waves, the waves are thought to go through each of the slits, and they retain a little bit of those interfering segments. And notice we have bands of bright and dark on the back wall where the waves interfered with one another. Now here again, we think these are now quantum objects in their animation, and as the waves go through, that whole wave leaves just one dot on the back wall. Now we have two dots on the back wall. Now three, and now we're going to have them fired more quickly, so you can see, aha, they build up the same set of interference, bright spots and dark spots. Now this is a rather subtle part to the two-slit experiment. If there's an observer, that little eye on the left-hand slit, gets to see what's going through, it turns out we do not get the same pattern on the back wall. I think we're going to speed this up very quickly and show we do not get the same thing. Instead, it seems to have become random again, which isn't exactly correct. But it's interesting. Now get out of this, if I can figure out how to do it, stop it. And let's come back up to a lecture given back in the 60s by Richard Feynman, who was just about to write his books, famous books on lectures in physics. And here he's telling students at Cornell about quantum mechanics. Let's listen to Richard Feynman.
There was a time when the newspaper said that only 12 men understood the theory of relativity. I don't believe there ever was such a time. There might have been a time when only one man did, because he's the only guy who caught on before he wrote his paper. But after people read the paper, a lot of people kind of understood the theory of relativity in some way or other. But more than 12. On the other hand, I think I can safely say that nobody understands quantum mechanics.
So that's a very important moment in the history of physics at Cornell, because what Feynman has just told you is that nobody understands quantum mechanics. I thought he had told us there was a time when only a dozen people understand relativity. He then said, well, he accepted the idea that there was a time when only one person understood relativity, and that's when Einstein himself figured it out. But very quickly, most of the world was able to follow his thinking on relativity, and it went well past 12 people rather quickly. But he complains nobody understands quantum mechanics. Now, it's my goal to, over my lecture series, upcoming lectures, it's going to take us some time, but I'm going to try to see why Feynman thinks. It's not understandable. And that's because it's fundamentally non-intuitive, and some things are mysteries, genuine mysteries. He says there's only one mystery in quantum mechanics, and I'm going to try to show what that mystery is that Feynman thought was behind other mysteries, and why he's right. The behavior of this mystery is something very difficult to accept. And I'm going to try to give you some ways of thinking about ways we might accept it, because we can start to visualize how it might be happening. All right, let's go back to...
Now, if you appreciate this, and don't take the lecture too seriously, that you really have to understand, in terms of some model, what I'm going to describe. And just relax and enjoy it. I'm going to tell you what nature behaves like, and if you will simply admit that maybe she does behave like this, you will find her a delightful, entrancing thing. So that's the way to look at the lectures, not to try to understand. Well, you have to understand the English, of course. But in any sense, in terms of something else, don't keep saying to yourself, if you can possibly avoid it, but how can it be like that? Because you'll get down a drain. You'll get down into a blind alley in which nobody has yet escaped. Nobody knows how it can be like that.
Here we go.
So then just let me describe to you the behavior of electrons or a photon in their typical quantum mechanical way. Now, the way I'm going to do this is by a mixture of analogy and contrast. If I made a pure analogy, we would fail. So it must be by analogy and contrast to things that you're familiar with. And so I make it by analogy and contrast first to the behavior of particles, for which I will use bullets, and second to the behavior of waves, for which I will use, say, water waves or sound waves. So we begin. First to discuss in a particular, what I'm going to do is I'm going to invent a particular experiment, and first tell how it would behave, what the situation would be in that experiment using particles, what you would expect to happen if the waves were involved, and then what happens when there are actually electrons or photons in the system. And I will just take this one experiment which has been designed to contain all of the mystery of quantum mechanics, to put you up against the paradoxes and mysteries and peculiarities of nature 100%. Any other?
So what we're hearing from Feynman is that there are mysteries. As I told you, he will eventually think there's really one mystery that can explain the others. But he tells us he's going to fire bullets through a wall with two slits in it, two holes he calls them, and then he's going to send water waves through. And when he sends water waves through, he's going to see the standard interference pattern. And when he sends bullets through, he's going to try to imagine how possibly the bullets, fired one at a time, can interfere with one another. And we'll come back at the other side and try to explain some of this. I may try to skip ahead. Bear with me if I don't get it going.
Situation in quantum mechanics, it turns out, can always be explained afterwards by saying, you remember the case of the experiment with the two holes? It's the same thing. And so I'm going to tell you about the experiment with the two holes, which is the general mystery, does contain the general mystery. I am avoiding nothing. I am bearing nature in her most elegant and difficult form. So I start with bullets. Then all the experiments are going to be in the same general design, so I'll draw it this way. Suppose that we have some source of bullets, which is just represent the source, which we call the source, and is in fact, in the case of bullets, a machine gun. Then we have a plate in front here with a hole in it for the bullets to come out of, and this plate, in the case of bullets, is armor plate. Then a long distance from here, we have another plate, which I'm drawing only a short distance because I haven't got room on the blackboard for everything, but this distance is supposed to be much longer in proportion to the width. Please expand that. That's a small point. And it has two holes in it. That's the famous two-hole business. I'm going to talk a lot about these holes, so I'll talk about this hole as number one hole and the other hole as number two. And I'm only drawing it in two dimensions. You can, if you wish to imagine these as round holes in three dimensions, but just say this is a cross-section. And then again a long distance away, but we'll draw it relatively short distance because of the limitations of this blackboard. We have another screen here, which is just a backstop of some sort. on which we can put in various places what I will call a detector. And we'll mark that detector. Which in the case of the bullets is a box of sand into which the bullets will be caught and we can count them. That's the detector for bullets. I don't want to have to redraw the experiment each time, so I'll label everything in this way, and then we'll be able to catch on to situations for different cases. And also, I'm going to do experiments in which I count how many bullets come into this detector or box of sand when the box is here, or here, or here, or here. And to describe that, I'll measure the distance of the box from somewhere down here and call that x, and I talk about what happens when we change x. It means only you move the doggone thing up and down. All right. Now, first, I would like to make a few modifications from real bullets into idealizations. The first is that the machine gun is very shaky and wobbly, and that the bullets go in various directions, not just exactly straight on and bounce back. And they can ricochet off the edges of the holes in these armor plates. And finally, well, let's say, for instance, that the bullets have all the same speed or energy if you want, but that's not very important. But the most important idealization in which it differs from real bullets is I want these bullets to be absolutely indestructible, so that what we find in the box is not pieces of lead of some bullet that's broken half, but we get the whole bullet, please. So imagine indestructible bullets, or hard bullets and soft armor plate or something. And now the first thing that we will notice about bullets is that the things that arrive come in lumps. When the energy comes, it's all in one bullet full of bang. If you count the bullets, there's 1, 2, 3, 4 bullets. The things come in lumps. They're equal in size, we suppose, in this case. And when a thing comes into the box, it's either all in the box or it's not in the box. It comes in lumps. More. If I put up 2 boxes here, I never get 2 bullets in the boxes at the same time. Well, if the gun isn't going off too fast and I have enough time between things, you see, slow down the gun.
So what we see here is that Feynman is giving us 2 elements of quantum physics that are started off with Einstein. His bullets, which are like Einstein photons when we get to light, are quantized. They are sent off one at a time, and you never find part of that photon of light in one place and another place at the same time. Instead, they come as a lump. You detect them entirely. We don't find one here and one there when we've fired off one. This will lead us to a big question that quantum physics likes to talk about these days that comes from Einstein's nonlocality. The thought is that when a particle travels off as a wave, because it has a probability of being here and a probability of being there, it's thought that it is in fact at 2 places at the same time. And this is, of course, a mistake, but a very popular mistake, which Erwin Schrodinger, in his reaction to Einstein's EPR work in 1935, said, well, it looks as if a particle could be in 2 states at the same time, because quantum states are always calculated as probable states. And this probability aspect led Einstein to not like it, and Schrodinger to take a suggestion from Einstein that we could imagine a system that could be both in one state or another, and he made the extreme example of a cat, his famous Schrodinger's cat, in which the cat is both alive and dead at the same time. These are extreme kind of interpretations or imagination about what quantum mechanics might mean if it's taken too literally. And one of the big things we're going to have to do is to follow why Einstein took us in that direction and led us to imagine such strange situations, and how it is that modern scientists have sort of exploited the strangenesses instead of looking for what Einstein himself hoped might underlie those superposition theories, they were called, which are in fact quite reasonable, but they sound intuitively very strange. Among the founders of quantum mechanics, besides Heisenberg and Born and Jordan, there was famously Paul Dirac. And Paul Dirac put together the math version, a very highly formal, very powerful version of quantum mechanics to do those calculations, which Heisenberg had first taught us to do, and then Schrodinger. But Dirac's method proved to be the method that I learned in the 1960s in textbooks on quantum mechanics. And Dirac was very clear that the description that we were able to give to a quantum situation was only a probabilistic description. And he formalized it as saying that a given state of a given small quantum system could have different probabilities. Let's take us over here to this picture, get away from Richard Feynman, although we'll come back to him as he gets onto his wave theory. We'll probably do that next week. And we want to focus on the notion that will come out of this wave-particle experiment, that when a particle goes off, initially thought of as a wave, and in order to kind of analyze first waves, then particles, we can say that as it leaves, and we don't detect where it is, it's considered as a wave. However, when we find it somewhere, then it's thought to be a particle. Now, if you'll stay with me here, I'm going to try to make a connection to information, my information philosophy, and the notion that information is an abstract quantity, whereas the naturalist, materialist, reductionist view of the world is that it's made up of material particles and nothing else, that there isn't anything immaterial which can be called a substance, the way matter and energy are substances. So let's now think in terms of what Einstein was studying in 1905. Light comes out of a central source and travels in all directions, it appears. That was the theory of light, and it showed the interference patterns characteristic of light going through two slits. But then Einstein discovered that if the light is very dim, and so it's going only at a very low level, today we would say that there's just one photon at a time traveling. That photon is always observed entirely, completely, the way Feynman was just telling us, that these bullets are always found as a lump. They don't break up and get part of them in one place, part of them in another place. And what does this mean? To me, it means that the wave picture in which the light leaves the central source and goes off in all directions is in fact, and Einstein was quite clear about this, really from the early beginnings, that the wave is simply a mathematical formula that tells us the probability of finding a particle or particles in different places. So as the wave has that picture we saw of higher and higher bumps in the interference pattern, what it's saying is that that wave-like interference pattern is just the probability of particles landing at those different places. So what we have is that the wave part of wave-particle is pure abstract information, mathematically calculable by Schrodinger's equation, but that it is not matter itself. Instead, matter is the particle or particles that get found in different places. So we can take that all the way back and say the wave theory of quantum mechanics or light and so forth is just an idea, and it's knowledge. It's in the sense that we can use mathematical equations, the Schrodinger equation, to calculate the amount of probability, to calculate and make a prediction of how many particles we're going to find at different places when we do our experiments. So once again, we have a theory, and the theory is the wave side of quantum mechanics, and it gives us predictions, which, when we go into experiments, are only statistical, but they are incredibly accurate. The more experiments we do, the more accurate the results become. But again, one hand we have theories, which are only information, give us information, which we can then use to predict how the universe is going to behave, considering that we organize it in a certain way. So it is really a tool that physicists use, that then engineers use in order to make things happen in the world. And then they do happen. However, they do not happen deterministically. As Einstein saw, to his great regret, they only happen statistically, which it would appear, and Einstein and others seem to agree on the fact, that we cannot say anything precise about an individual particle or an individual experiment, because the theory part is only giving us probabilities of what will happen to individual particles. The theory is a statistical theory, gives us probabilities. And experiments, when done in large numbers, give us the results that apply to large numbers of particles. And when you have a large enough number of particles, they look very continuous and like light, which seems to be continuous, and it's indistinguishable from the old wave theory. But that's different when we go down to the quantum level. And at the quantum level, when we look at one thing happening at a time, and that includes the light in this experiment we've just seen, or the two particles being separated in the entanglement theory. We're now talking about two specific particles, and yet all we know about them is what they do statistically. So one way people have thought about that entanglement experiment is that each of the particles is in a statistical combination, or a superposition of one particle. Say in entanglement we often send the two particles off in two states. We imagine them as electrons spinning up on the one side and spinning down on the other side, and that this down and up situation will be discovered to be one up and one down at the end of the experiment, but that in between times, since the theory is only a statistical theory, we argue that each of the two particles could be up or down, 50-50, for example, just as we argue that the cat could be dead or alive with 50% chance of living and 50% chance of being dead. But notice that, and this is sort of an Einstein criticism, a point of view we'll get to, we never see a dead and live cat at the same moment. All we really see is when we do large numbers of experiments, we see so many, say 50 out of 100 dead, 50 out of 100 living, or it might be 48 or 52 or whatever in different experiments. It is, to me, quite illegitimate to reach the conclusion that the probabilities mean that the cat is dead and live at the same time. And similarly with the particles traveling apart in these entanglement experiments, to say that they are both randomly up and down is to suggest that they might be both up at the same time or both down at the same time, which would violate the principle of conservation of spin in this case. Einstein knew even in the beginning that questions about whether things could change what they were doing would violate conservation principles. And we'll find that that's a great insight that will help us to understand more these mysteries like entanglement and the two-slit experiment, and ultimately the collapse of the wave function. And we'll come back to those in coming weeks. But in the meantime, this was my first week. So I've been making quite a few mistakes as I switch my switcher around. Remind you that what I'm doing here in this room is rather complicated for me to give you a movie playback today and get from one screen to another comfortably but I hope I'll be able to do that better in the future. So I hope to see you next Monday. Thank you very much.